I would like to present the recent status of PICOLON dark matter search project. This picture is our newest sodium iodide detector, which is installed in Kamioka Underground Laboratory. We need to verify the Tama Libra result by sodium iodide detector. They have reported more than 13 cycles of the annually modulating signal as shown in this figure. This figure shows the annual modulating event rate between 2 keV and 6 keV electron equivalent. The 13 cycles data gives about 12 sigma significance of the modulation. To prove the result, we need to the same target, the sodium iodide detector with less background. So the potassium, uranium series, and thorium series are the main origins of the background in the sodium iodide scintillators. Our target purities of these isotopes are listed here. The concentration of 210 lead is quite essential to give high sensitivity to dark matter search. So we set goals by a very challenging value of 15 microbecquerel per kilogram. The purities of other sodium iodide projects are listed here. These values will be updated by this conference. The remarkable purity was obtained by Dama Libra crystals. We need to develop a purer sodium iodide crystal than the Dama Libra's one. So you know that the reduction of 210 lead is the most critical and challenging task. So we investigated the purification methods. As the Xine group reported, the Re-Crystallization method is quite effective in removing potassium ions. However, it is not so practical for lead ions because lead is not water soluble. This picture shows the schematic of the Re-Crystallization method. We get the saturated sodium iodide powder in the saturated sodium iodide water solution. The potassium ions move to the water and removed from the sodium iodide powder. On the contrary, the lead ion is not soluble in water. The lead ions, in this case, mainly in lead iodine, remains in the sodium iodide powder. The remainder lead makes the 210 lead background. We need to search for an appropriate method to remove lead in the sodium iodide solution. So we experimented to confirm the lead removal effect of the resin. We added lead iodine to an aqueous sodium iodide solution. Next, we poured an aqueous sodium iodide solution through various resins. The resin A was used for our previous works. Resin B is a resin with the similar properties of A. The resins C and D are investigated in the present work because we obtained samples as effective resins for removing lead. The lead concentration in the sodium iodide aqueous solutions were measured by ICP mass agent 7900 in Osaka University. The measurement result is shown in this figure. The red line is initial lead concentration. The green dots are the lead concentration after purifying by the resins A, B, C, and D. Resins A and B had almost no lead removal effect. On the other hand, the lead concentration of resin C and D was very effective. And the C is effective reduced about 1/20, and D reduced to 1/30. So we decided to apply regions C and D. So I will show you the actual purification process. The principle of recrystallization is shown here. The first, we dissolve the sodium iodide raw materials in water at 100 degrees of Celsius to make a saturated solution. After confirming it is completely dissolved, we cool it slowly to room temperature with stirring. As the temperature decreases, the solubility decreases, and the sodium iodide precipitates. On the other hand, natural potassium remains in solution because it is overwhelmingly low solubility, large solubility. Okay. The flow of the one recrystallization is like this, and we repeated twice. This is how an aqueous solution sodium iodide is passed through the region. Region C and D is put here. If the region absorbs lead ions well, it can be expected that the concentration of the lead in this sodium iodide solution will be decreased. So this is a picture of our constructed purified sodium iodide crystals. Ingot number 85. The diameter is 3 inch and the length is 3 inch. As you can see, the clear crystals was created. So alpha emitting isotopes contained in the sodium iodide crystals were measured by the pulse-shape discrimination method. The above events, these events are due to the beta rays and gamma rays. And alpha rays are observed these logs. So you can see the alpha ray events is very low event rate. So this picture is compared the alpha ray energy spectrum between the our present result and previous our purest sodium iodide crystals. The blue spectrum is a result of our previous purest sodium iodide. You can see the peaks due to the progeny of the 226 radian. 210 polonium was will be observed around here, and in this from the energy spectrum, the ingot 24 contains 100 microbecquerel per kilogram of 226 radium and 50 microbecquerel per kilogram of 210 polonium. And as you can see, the counting rate of the ingot 85 is significantly reduced. No significant excess for 210 lead events observed. So we set limit on the 210 polonium, and it is about 6.7 microbecquerel per kilogram. It is upper limit. So we have successfully developed a highly radiopure sodium iodide scintillator. The severe background origins, potassium, thorium series, uranium series, and 210 lead were successfully removed by combining the recrystallization and resin methods. All values of radioactive impurities in ingot, crystal ingot 85 were below our goals. In this year, we verified the reproducibility of the purification method. Ingot 94 the data is taken now, and very small statistical accuracy, but the preliminary result gives a well reproducibilities. So the current background of ingot 94 is shown here. But very preliminary. The background rate is about around 2 and 4 per DRU, but it is without any coincidence. So there are many prominent peaks due to the 125 iodine peaks, cosmogenic one, but they will decay with a half-life of about 50 or 30 days. So after a few months, these peaks will decrease. So prospect. Having established a method for purifying sodium iodide, we started manufacturing large volume sodium iodide modules. Each piece is 5 inches in diameter and 5 inches long. These figures right and center images of 4 large sodium iodide modules assembled. A shield is constructed in the Cameron area of Kamioka Underground Laboratory, as shown in this picture. So our student is constructing. Let me summarize my presentation. We have established a method for purifying sodium iodide scintillator. And it has become possible to mass produce of sodium iodide crystal with sufficiently high purity. The concept, so the reproducibility of the purification was verified by 2 pieces. The 210 rate is less than 5 microbecquerel per kilogram. Uranium and tritium series is 10 ppb. And natural potassium is less than 20 ppb. So enough high purities. So from next years, the construction of large volume sodium iodide will be started. And test experiments start from next years. Thank you very much.